This meeting is being recorded.
Okay, so again, hello everyone to another GOAT seminar. Today's speaker is Nikolaos, and he will be talking about some digraph coloring and distance to acyclicity. Thank you.
Thank you for the introduction. I am, you can call me Nikos. I will present you one of my previous work presented in Stacks 2021, which is related to graph coloring, and in particular in direct graphs, and what relation it has with acyclicity on these graphs. This work, it was with my previous supervisor, Arat Khan, and another colleague, Michael Lambis, from University Paris Dauphine. Okay, so first I will present you what the problem is, and which is its relation with the classic graph coloring. Then I'm gonna give you some existing and trivial results, and then we're gonna discuss about parameterized results based on parameters that are related to acyclicity, like directed feedback vertex set, feedback arc set, and tree width. And in the end, I'm gonna give you a simple exact algorithm for tournaments. So, which is the problem? In the classic graph coloring, when we have some vertices, we want to give colors to those vertices such that two adjacent vertices have different colors. For example, here, all the vertices need different colors because all of them see each other. However, this idea is not really easy to be extended in directed graphs, because if we keep the same idea about adjacency, then we completely ignore the direction of the edges. One possible extension of the graph coloring is that you may want to give colors in the edges such that there is no monochromatic cycle in the graph after we color it. So, for example, in the right, you can see that this graph now it's too colorable because the two vertices in the top may share a color as they don't give us any cycles. So this coloring is a generalization of the classic coloring, because in several cases we may have parallel edges that have different directions that create a cycle, those usually called digons. And if you replace every edge of a graph with a digon, then you're forcing the directed graph to have the same colorings exactly as the undirected graph. This coloring was introduced by Victor Newman Lara, 1982, where they discuss about the dichromatic number of a graph. And obviously, because of this relation between the two, the undirected and the directed setting, the dichromatic number is at least as hard as possible as the original graph coloring. Okay, so formally, what we want to do is to partition our vertices of the graph into k sets, such that each one of those sets give us a DAG, a direct acyclic graph. So another example here. So in this graph, we may want to check whether this graph is too colorable or not. And if I'm giving you some time, you're going to realize that this is too colorable, because we can color the vertices to the left side with the color blue, to the right side with the color red. And you can see that the blue vertices, the graph they give us, it's acyclic. The same with the red vertices. Hopefully this is become clear and what the problem is. So let me start with some existing results regarding this problem. And first, we can see that the problem is NP-hard for directed graphs with maximum degree 2k plus 2, which comes exactly by the observation I give you before, that we can replace every edge of a graph with digon, and then our coloring is the same as the classic coloring. And we have a generalization of Brooks' theorems due to Mocha 2010, which says that, okay, the problem is in P when the maximum degree is to K. And finally, it's already known that in tournaments, the problem is NP hard, even if we want to decide if there is two color. So we don't really have many results regarding parameterized complexity of this problem, except of the trivial parameterization by the number of colors, which is obviously NP hard, even if the colors are only two due to tournaments. So what we decide to do is to consider parameterized parameterization of this problem. And first we discussed about directed feedback vertex set, which is a natural parameter for this problem because we care about acyclic subgraphs. So a first really obvious observation here is that if the graph is acyclic, is one colorable. And whenever we have a feedback vertex set, recall that feedback vertex set is the number of vertices that if you remove them from a graph, then the graph becomes acyclic. So if the feedback vertex set is of size k, then we can always color the graph with k+1 colors, because we can use k colors for the feedback vertex set, and the extra color, it can be used for the rest of the graph, which is now acyclic. Okay, so based on those results, there's a question arises, the fact that, okay, what happens if we want to color a graph with k colors and the directed feedback vertex set is of size k? So here we managed to prove that this is NP hard even if we have only two colors and the directed feedback vertex set is of size 2. In particular, we present a reduction based on a restricted version of 3SAT. In this restricted version, you have that each literal appears only at most 2 times positively and 1 times negatively. And maybe I'm saying something wrong, sorry. Yeah, okay, this is correct. And each clause has only either positive literals or only negative literals. Okay, so let me try to explain a bit the construction. For each clause, we're creating a path that the L vertices represent the literals, the W vertices are just connectors. And then what we are trying to do is create paths for all of those things, and then connect the positive and the negative literals of the same vertex with another kind of paths. So the idea presented here, so you can see that for those two clauses here, we're creating two paths, two horizontal paths, that the vertices here represent the literals. There are some connected vertices, and for each appearance, positive and negative appearance of the same variable, we have those vertical paths that still have some connectors. Now, if you think a bit, you're going to realize that if we create the whole graph, this is acyclic. Now we need to force in new colors. So we're going to create a palette for our graph, and this palette for the k is equal to is just 2 vertices connected with a diagon, those 2 parallel edges that have different directions. So those 2 vertices must have different colors. And what we're going to do is forcing one color to represent the true literals and one color to represent the negative literals. How? First, with the horizontal paths, we are forcing a cycle that includes the second vertex of the palette. You can see that we have this cycle here, and we connect all the middle vertices with the other vertex. And for the other paths that connects positive and negative literals of the same variable, we want at least one of those to have positive and the other to be negative. So it's one false and the other is true. So we need to force to have different colors, and we create those vertical cycles here. Now, why all of this holds? The idea again is that those horizontal paths, we're forcing the middle vertex to be red, let's say, and we need to have at least one vertex that it's green. And in all vertical paths, those to the right are the vertical paths, we need at least one of the two variables to be false. So the idea is exactly this. So you're forcing, if there exists a satisfying assignment, then you can color those vertices with the corresponding colors, and you are okay. And if there exists a two coloring, then you can see that each clause here, it has at least one true literal, and for each variable, you know that you don't have all the literals to be true. So we are okay. Now, if you want to generalize this idea for k colors, the only thing you need to do is to extend your palette. So we can just add vertices and connect everything with those vertices with digraphs. So this new vertex, one new vertex is going to represent one new color, two new vertices, two new colors, etc. So you can generalize it for any size of feedback vertex set and any number of colors. Okay, so here we have a really interesting dichotomy based on those two results. And the thing is that, okay, like I said in the start, we have every graph that has directed feedback vertex set of size k to be k plus 1 colorable, but it becomes MP hard to decide if it's k colorable. So the k plus 1 is the best that we can say in polynomial time. Okay, because this becomes really hard for this problem, we try to consider more strict graph classes. And first we said that, okay, we're gonna bound the maximum degree. And still, if you play a bit with the previous palette, you can create a more complicated one, and so that the problem remains MP hard, even if the maximum degree is 4k minus 1, while it becomes tractable if the maximum degree is 4k minus 3, yeah, 4k minus 3, and the idea is that you can color the close neighborhood of the directed feedback vertex set, and then you can extend it. And that's what's basically I'm saying here about the palette and the extension. Okay, so with bounded degree, we cannot do too many things and bounded feedback vertex set. So we decide to consider, also the second give us a consequence that in those graphs, the k-Digraph coloring is FPT parameterized by k, when you have both directed feedback vertex set of size k and maximum degree for k minus 3. Okay, so then we decided to consider the directed the feedback arc set. The directed is not needed here. And the feedback arc set is a set of arcs. When you remove those arcs, then the graph becomes acyclic. And again, we managed to show that the problem is NP hard if the feedback arc set is k square, while the problem becomes tractable if the feedback arc set is k square minus 1. And again, we can do it based on the vertices related to the feedback arc set. Before we didn't need the part of the vertices because it was vertices. So yeah, the problem, the graph is k colorable if and only if the induced subgraph by the vertices of the feedback arc set is k colorable. And the second result is based on the induction of the number of colors. It's not something really complicated. while the first result still is a bit more complicated palette in order to force the feedback arc set to be of size at most k squared. Okay, and again, the second thing, it gives us that the problem becomes FPT in graphs with maximum degree, with feedback arc set of size at most k squared minus 1. And again, you can see here, you can see again we have a dichotomy because for feedback arc set of size k squared, the problem becomes NP hard. Well, if you have it smaller, then it becomes tractable. And this is in general really interesting from my point of view. Okay, so what we can do? Because we failed to find a directed parameter related to acyclicity in order to set the problem in FPT, we decided to consider the trig width of the underlying graph. And what we managed to solve here is that, okay, there is an algorithm that you can calculate the number of colors you need in order to color the graph in k to the power of trig width times trig width factorial and the polynomial of n, which is not really nice running time. And notice here that the number of colors is always bounded by the trig width. So this is FPT by the trig width. So we consider whether we can reduce this running time because this trig width factorial there is really irritating. There is no reason for it to exist. However, we saw that this is not possible. And even if we consider two coloring, we managed to show that there is no algorithm that runs in trig width to the power of small o of trig width unless the exponential time hypothesis is false. And for those that don't know, the exponential time hypothesis is a hypothesis that says that 3-sat cannot be solved in to the small o of m plus n. Not exactly this, but this is enough for us. So what is the idea? The idea is that we're going to start from a 3-sat instance and we're going to create a graph with number of vertices to big O of n over log n times m. And the trig width is going to be big O of n over log n, and we're going to show that this instance is satisfied if and only if the graph we're going to create is two colorable. And you can see that if you try to replace here in the running time the values I have give you, then you can see that, okay, this would give us a better algorithm from 3-sat, and we don't expect that. Okay, so which is the idea of the construction? Here becomes a bit technical. So first, we consider the set of variables, and we divide this set to log n sets. And for each one of those sets, we create a set of vertices vi. Now, we connect all the vertices of all of those sets with a universal vertex u in order to force them to have the same color, because we consider two colors. Okay, so each one of those is going to have the same color. Then we need to find a way to represent the assignments for each one of those sets. The idea here is that for each one of those possible assignments, we define an ordering. We define an ordering, and then we create another set, which is here, the Sij sigma, which is related to this assignment, the clauses that satisfied by this assignment, and the set of variables. So we connect the two sets in the order that presented by the ordering we have defined, and this specific, let's say, path represent this specific assignment for the variables in Xi. Now, what we need to do is to relate those these sets here with the clauses, and that's why we have the thing that this satisfies a clause. Now we take all of those sets that are related to a specific clause, and we try to create a cycle. Now, how we're doing this, we decide an ordering for those sets, and we are using those new connector vertices, which every vertex of this set connected to this one and continues. So this creates a path, a cycle. Now, the idea is that because we want to have a two coloring, we cannot have all of those sets the same color because we have a cycle. Okay, so let me give you a bit the high level why this works. Assume that we have a satisfying assignment. Then we are going and color all the sets, all those sets that related to the assignment that we have with one color, and the other sets with another. So we have destroy all the cycles related to clauses. Now this becomes a bit more complicated because we have this part here. Now you need to see that because of the ordering we have selected, each part that is colored with the same color, and we're going to use the same color also for this set here. This and this will have the same color if this is the satisfying assignment we have selected. Then this is just a path which is acyclic, and this holds for each one of those sets that we have partitioned. So each one of the VI related to one specific S that has been colored with the same color. So we don't have cycles of the same color. Now we need to do the reverse, and let's assume that we have a two coloring of the graph. Then first we need to observe that all of those sets have the same color, let's say black, and with the way we have connecting some things, those sets those are white, so at least one set of those must be black in order to destroy all the cycles. All the vertices must be black. If for each one of those sets we have at least one white vertex, then we can create a white cycle. Okay, so one of those sets is whole black. Okay, now we need to use this set in order to give the satisfying assignment for the literals, for the variables. So we just need to use the ordering we have selected and relate it to the assignment we have set. Now observe that we cannot have two different assignments for those for these variables here, for variables that are represented in this set, because this means that we have two such sets that are colored the same, and because they're represented by different orderings, we have a cycle. So each variable has a unique assignment, and then because we have destroyed all the cycle related to clauses, each clause is satisfied. Okay, I know that it was really technical. That's finished. So I promised you that I will give you an algorithm for tournaments, and I'm going to start with proving or explaining most how you can decide if a tournament is two colorable. And okay, we have a problem here. Okay, so the idea is based on the fact that if the tournament is not acyclic, then we always have a triangle that we can find easily. So what our idea does is consider this triangle and take all the legal possibilities for this triangle. So if you have a triangle and you want to color it, then you know that you cannot use the same one color in both, in all the three vertices, obviously. So this gives us far less options, and basically this gives us cubic root of 6 for each one of the vertices, because if you have those three vertices, you have only 6 legal legal colorings, because you have 8 possible colorings, but you need to remove the colorings that are monochromatic. So it's instead of 8, it's 6. So this gives us this running time, and this is interesting mostly because we didn't know if we can actually coloring with less than 2 to the power of n time. Okay, so what we are doing is coloring those triangles, consider all the possible options until the remaining part is cyclic, and you can give just one color for that. Now, this can be generalized a bit and give us this much more ugly running time for the k colors. But again, the idea is the same, because you have k colors. It's k to the power of 3, the possibilities for the triangles, and you need to just remove the ones that are monochromatic. Okay, perfect. And this is obviously just decides if it's k colorable, then you just need to run it for all the possible cases until you find the minimum that it's satisfying this, and you can color the tournament. And more or less that's it. And let me try to conclude what I have presented you. I don't know how much time I have spent. Sorry if it was too short. Okay, so what we did was we saw that the problem is that the graph coloring is NP hard for directed graphs of directed feedback vertex set of size k, even if the maximum degree is for k minus 1. We saw the same about feedback arc set of size k square. We saw that the problem becomes FPT when the directed feedback vertex set is k, but the maximum degree is at the most for k minus 3. And the same becomes with feedback arc set of size k square minus 1 and with 3 width. And here, let me say that, okay, those two first dots becomes obvious if someone knows that the directed feedback vertex set is FPT by its size, and the same for the feedback arc set, otherwise it's not obvious. Finally, we present in a lower bound for 2 coloring, and I think that it's missing from here, but I give you the k coloring for the tournaments. And some open questions here. It would be really interesting to consider other undirected structural parameters, because most of the directed ones, I say directed, but most of the directed ones are bounded by the feedback, by the feedback arc set, at least those that are related to acyclicity, like the directed 3 width, or the directed version of 3 width. Then it would be really interesting to see what happens if we allow higher values of directed feedback vertex set, because we saw that the problem becomes tractable if the directed feedback vertex set is k and the maximum degree is 4k minus 3. But the problem becomes also tractable if you have unbounded feedback vertex set, and the maximum degree is 2k. So it's interesting to see what happens in between. What happens if we allow directed feedback vertex set of size k square or something like that. And finally, it would be interesting to see whether the problem becomes easier if we consider the partitions to be almost acyclic instead of acyclic. So this is another idea that maybe give us a new problem. So instead of asking to give colors and each color give us an acyclic graph, then we may ask for graphs that have a really small feedback vertex set, a directed feedback vertex set, or even properties related to the underlying graph, like the bounded feedback edge set. That's it. Thank you very much.
Are there any questions? I had, but I forgot it. I had two. I think the first one of them will take offline, and the other one was well with this. If you don't have other questions, with this construction of anti-hardness, you showed that it would create cyclicity where somehow all, like for these clauses, you had the cycle. If it were all red, you would create a monochromatic cycle. For literals, you had a green cycle that would be created.
Yeah, give me a moment
if there was
to find it.
If there was like a positive evaluation of both occurrences. Yes.
This one.
Yes. But I thought you are reducing from like the version of SAT where all clauses have either all positive or either all
literals. Not necessarily. It's not necessarily everything after the after the assignment. It's not everything true. The literals.
So literal occurrences are all like either not negated or all are negated. So I thought that in this construction you would have somehow different construction for these two types of clauses.
You don't need it, because the only thing that you care is that deciding which one is going to be true. So if I am giving you that, okay, the no xi is true, then you know that xi is false. But
okay, so in that red cycle you need at least one green, which means that this
exactly
true. And for
this one,
you said that just both cannot be true at the same time.
Exactly.
What about having them both false?
You don't care. If you can satisfy your formula, even if those are both false, then set one of them true and you are still okay. So you just don't need this variable, basically.
Are there any other questions? Maybe first correct me if I'm wrong about the algorithm on tournaments.
Yeah.
So you look at the triangles, which are cycles, and then you try to find a coloring that is not same on the triangle. Can we have a slightly better algorithm if we look on slightly bigger graphs? For example, if we have two triangles that are connected onto vertices, aren't the number of possibilities more restricted? So
you are saying that just to search for something like different and follow that? Yeah, probably. But you need to find an argument that guarantees the existence of those things.
Yeah.
But yeah, if you find something more complicated and have less options per vertex, yes, it's going to give us a slightly better algorithm. But the problem is the guarantee. While the triangles are guaranteed, the tournament is acyclic.
Okay, let me jump in because we are on the correct slide for the second question.
Okay.
So for this, I understand you look for oriented triangles.
Yeah.
And choosing one of good colorings for just this triangle.
Select, take all the possible options except the non-valid one.
Yes. Okay.
So for this triangle, you have basically 6 options.
Yes. That's clear.
But what do you do then? Do you decide this coloring and remove the triangle from the graph, or what exactly?
You can just color it and keep it there,
Yeah.
and check if the uncolored part is acyclic and continue.
And if it's not?
If it's not, you continue find new triangles, color them.
So do you find the triangles that all three vertices are uncolored?
Well, you may play a bit and find some triangles that are almost uncolored, but still the possibilities is less than this.
Oh.
Yeah, because if it's if you find a triangle that has, okay, if it's just one vertex uncolored, you can basically ignore this triangle. You don't really care about this.
It's decided. No, it may not be decided.
Yes, but it's gonna be decided later if you continue the process.
Okay, so there is something more,
yes.
more complicated.
So basically, you care about mostly about the triangles that are completely uncolored. So if you color all of them with all the possible options, some of them are okay, and then you have an acyclic part which you can color easily, unless something is forced and you're coloring the parts that are forced. So those that are not forced, basically, that one vertex that we're discussing, basically it has either two options, or existing in a monochromatic cycle, so you are forcing a specific color and finish, or all the colored parts are not forcing the color for this vertex. So you can color it with any color you want. So you don't really care about these weird situations that you have those triangles that are partially colored. In the case that you have, again, two uncolored vertices and one colored, you can do similar arguments and see that it's not something. So basically, you prefer to color uncolored triangles.
Okay, there's an online question. Are you going to read it?
Okay, so I just wanted to have one small remark, but I guess you're aware of that already directed feedback vertex set requires slightly super exponential time when computing on graphs of bounded trivet. And I was wondering whether there was a way to use that to prove your result, your lower bound. And yet another question was, so you know that it can be solved fast on graphs of bounded trivet. And the question is whether you consider graphs of bounded clique-width.
So about the first one, I haven't considered that, so I'm not sure if you can use it, but it's probably interesting to consider it. Well, for the second one, the same. I haven't considered click width, so I am not sure. Well, I have not really worked on click width, so I'm not really sure what I can answer.
Does anyone know whether there is a directed analog of twin width?
Not really.
Are there any more questions for our speaker? Well, if that's the case, let's thank the speaker again.